so that we can pick up those later on in the after his talk is completed. Okay. With that, Sunil, over to you.
Yeah, thank you so much, Chandu. Thank you so much for the nice introduction. And you seriously need to stop lying. I did not give you 5 pages of my introduction. It was just maybe couple of lines. So, but I know I love you, Chandu. Thank you so much for inviting me here today. So I think I'll stop my video and just I hope everyone can see my slides.
Yeah,
Yeah,
it is able.
yeah,
Yes, we can see your slides. No
yeah.
problem.
Okay.
So
So
I request all maybe video you can switch off so that bandwidth will be nice,
yeah,
so
yeah,
no disturbance will be there.
yeah.
All right. Thanks.
Okay, thank you so much. So, as the the topic is very apparent on on the slide, I'm going to talk about the future treatment as far as the water purification or drinking water or any water treatment is concerned. So, thank you again, Water Quality India Association, for inviting me. So, let me see how it works. Yeah. So the presentation layout is, I'll talk about a little bit of history. As you know, those who have attended my previous talk, so I really like or love to discuss history, because history is like a roots to your present development and future development. Then what are the present issues, and then future I'll be talking about on the water treatment front. So future I have mostly split into two sections, and it can we can understand broadly the water treatment through desalination and non-desalination. So let's try to understand. So begin with the future. Sorry, the history of the filtration. I just want to get rid of this the top thing. I don't know how to get it, how to make it disappear, so that anyway we can live with it. So yeah, so as usual, I like to start my talks showing some roots, showing some Indian roots to whatever treatment technology, R&D, and all that. So around 6,000 years back, Indians and Greeks, they started understanding that if they, pass water through charcoal or they do some boiling, they can purify the water. So that was around 6,000 years back. Then around 3,500 years back, Egyptians somehow they understood that okay, if you use alum, you can settle the suspended solids in the water, and that's how you can purify the water. Then in around 300 years back, there's a huge gap from say 3,500 years back to 300 years back. So people have started the both the concepts, like passing through charcoal, sand, and using alum, and that's how they started removing the turbidity or impurities from the water. And then in 1800, people also detected that there are bacteria in the water which can cause different diseases, and they wanted to find some solution to get rid of these bacteria and all that. And then in 1900, we kind of started talking about membranes and different other different water treatment technologies which can remove whether it is bacteria or turbidity or any other suspended impurity. So this timeline seems to be very very simple, but what we need to understand here is the take home message here is, when we started, for example, 6,000 years back, it is not that you only needed the charcoal or you did not need any hi-fi or rocket science technology there. It was not needed because by then you did not start messing up with the water. Now as you go along with the timeline, you can see the impurities in the water are increasing, and that's how we came up with the solution. Okay, now it is having a bacteria virus, so come up with something which can remove that. So on the same timeline, you can see there is a industrial development in the human race, but at the same time we have started messing up the water. So when we come to the very recent 20th century, so by that time it is not only the pathogens, turbidity or other impurities, but we have all the chemicals in the water, volatile organic chemicals, pesticides, what not. So now, till the maybe 1960s 70s, you started putting everything, you started finding everything in the water. Now what? Now there is everything in the water except water. Now we suddenly have started saying that there is no water at all. So why is that? Of course, if you look at the recent history, if you try to see the bottom left hand side image, so around two-thirds of the natural wetlands have disappeared since 1900. Two-thirds. We are putting around 80% of the wastewater without treating, we are putting back it to the oceans or rivers. So that is the price we are paying for our so-called industrial development. By 2025 we will have around 1.8 billion people who will face absolute water scarcity. So the the bottom right figure, you can see the map. So all these countries will be like water stressed countries. Of course, India is also one of them. So now, till the time we were talking about treating a water which is available to us, a fresh water available, maybe river, lake, whatever natural source. Now the focus is suddenly how can we recycle the water? And since we have messed up too much with the natural source of water, now we are focusing on the sea water. That water is of course there, like 97% of the earth is sea. So now we are exploring that how can we mess up sea. So prominently now we are talking about water recycling, sea water treatment or water harvesting. That's the only option left with us right now. So, okay, now coming to the present or future, as I said, I have split this presentation in two parts, desalination and non-desalination. So it's not that only desalination can do the justification to explain the future, but coincidentally, it covers everything. So it will cover all your other technologies, whatever happening now, what will happen in the future, and if it is desalination, it might or it will end up needing other technologies like whether it is nanofiltration, ultrafiltration, microfiltration. So I have split the presentation basically in two parts, desalination and non desalination. So if you want to understand the desalination, primarily there are four different ways you can do desalination. The first is thermal energy. So when you talk about thermal energy, to for understanding it in a simpler way, it's mostly the distillation or evaporation techniques. So in thermal energy, of course, there is one membrane distillation is lying here also, because though it is a membrane, but it needs a feed to be heated to some 75 to 80 degrees. That's why it is lying under thermal energy. Mechanical energy, of course, we are talking about all the RO membranes, NF membranes, or any other membrane. So electrical energy, electrodialysis or capacitive deionization, and then chemical energy, the ion exchange resin. So let's try to understand what is going to be a future of water treatment as far as the membranes are concerned. So, and since I'm just assuming that most of you attended my previous talks, and that then I'm just jumping to the topic without explaining what reverse osmosis is. And of course, all the members here know what reverse osmosis is. So at present, there are categorically there are four types of RO membranes: the tap water RO, brine water, sea water, and ultra high pressure RO. And in the bracket you can read what is the limitation of TDS ppm it can treat. So it varies from say 2000 ppm to 50,000 ppm. And the recovery, the water recovery in all these four types of setups or membranes varies from say from 70 to 50%. So that's the max. So on an average, to be talking about practical achievability, it is around 50%, for example. Okay. So
So
the
Sunil, this is recovery is 70 to 80. It is 70 to 50. It's showing. This is
uh
this error, no?
yeah, it is 70 to 50.
Okay.
Yeah. Does it show 80 there?
No, no, it's not there. Because see, when just I thought of it similar because usually when we write a range, we write from the left side 50 to 70. So you wrote back, just
Yeah,
50.
yeah,
So
yeah.
I thought of
Yeah, yeah,
it's an
some
error or
typo. Some typo. You just consider maybe 50.
what? Okay.
Yeah.
Okay. Please go ahead.
So yeah, so the let us understand, in order to understand the future of RO, we need to understand the economics of RO. So mostly I'm talking about a typical seawater RO plant here. The capex accounts up to 53%, then the OPEX is around 47%, and of this 47% OPEX, the energy consumption is up to 69%. Okay, that's the present thing. So what are the triggers for the innovations as far as RO or replacement of RO is concerned? So right now the major issues are fouling, whether it is biofouling or colloidal fouling. The energy consumption per meter cube is relatively high. The fluxes are very low. We are talking about 3 to 15 liters per meter square per hour. Chlorine resistance is very low, up to 1 ppm, because you need to have a chlorine resistance in order to clean your membranes or backwash, or forward or chemical enhanced backwash and all. So these are the triggers for the RO membrane to be taken to the next level or do some future developments in the RO. So the first thing I'm going to talk about RO modified by using the nano embedded materials. So I'm just see my the idea in today's talk is to just touch upon all the developments or the potential technologies which people are working on, or which you can see in the market maybe in very near future, like maybe 6 months time or 1 year's time, or in next maybe 3 4 years time. So I'll just briefly touch upon the technical aspects of it. So if you want to discuss in detail the technicalities, that we can have that discussion one on one. So the RO name is a membrane, RO membrane, mostly as you can see on the picture on the right hand side. So the top layer is coated with some
So there is some bandwidth.
maybe
Sunil, not able to hear properly.
yeah.
Now it's okay. Go ahead.
Just a minute. Seems like some network issues at mine.
Yeah,
Yeah,
yeah. Please go ahead. We can hear.
yeah. So the RO name is like, yeah, you're coating the RO top surface with some nano embedded materials like oxygenated silver or oxygenated graphene. And what it does is that it is increasing the water flux, salt rejection, then it improves the fouling behavior of the membrane, and also improves the chlorine resistance. So this is something like people have been working on it since long, and now I think it should be there in the market maybe in a couple of years time. Now to understand the next level of development happening on RO is forward osmosis. So this is almost, I mean, there are a couple of companies who are already offering this, and in India also there are a couple of groups who are extensively working on this. There are some CSIR labs in India who are working on this. So forward osmosis is, in order to understand the forward osmosis, you need to understand what is the reverse osmosis. Basically, osmosis is, as you can see in the left hand side beaker. So there is a semi permeable membrane in between, and on the left hand side compartment there is water with less amount of salt or solute, and on the right hand side the solute concentration is very high. So as the what nature tries to do, it always tries to find an equilibrium. So as a natural phenomena or thermodynamic phenomena, water from the left hand side will try to go to the right hand side, so that the solute or salt concentration on both the sides is equal. So this is the osmosis. So in the reverse osmosis, we reverse this by applying the pressure on the opposite side. So in forward osmosis, we are going to use this concept only, that how can I modify the right hand side or permeate side of the membrane, so that it automatically draws the water from the feed side. So that is forward osmosis. So how does it look? So it looks something like that. So the feed solution is feeded to the feed side of the forward osmosis cell, and on the permeate side there is something called a draw solution. So we are purposely keeping the solute concentration, salt concentration on the right hand side higher, so that through osmosis the water is drawn to the right hand side towards the high solute concentration side. And then this so called draw solution, the red colored solution you see here, is fabricated in such a way that at say certain temperature or with some mechanism, it coagulates the solute or on the permeate. So this is, there are many issues like membrane fouling, reverse solute diffusion, concentration polarization and all that, but it's a relatively low pressure operation and it holds a very huge potential. So that's something people are aggressively working on, and there are a couple of companies who are already offering this solution. Now the third thing is osmotically assisted RO. Now osmotically assisted RO is something which is a combination of RO and forward osmosis. So the picture here is a little bit I would say busy or messy, but what we do here, we are basically arranging different, for example, RO membranes or RO skids in such a manner so that it is working as a normal conventional RO. Along with that, we are maintaining some TDS levels purposely in the permeate flow so that we exploit the osmosis pressure also. So it's basically, you don't need to understand this picture here, it's very complicated, but it is a combination of RO and forward osmosis. And this somehow this holds a capacity, this holds a potential of taking the recoveries up to or even more than 70%. Now the fourth thing which people are aggressively working on, and this you can, there are a couple of companies who are already there in the market who are offering the commercial solutions, and this is also very close to me because I'm personally working on this. So it's a membrane distillation. So these are the membranes which are used for the distillation or water purification or removing the salts or minerals from the water. So what it does, so these are not like RO membranes. These are maybe similar to the ultrafiltration or microfiltration membranes. So these membranes have pores which are bigger in size, like micron. We are talking about maybe 40-50 nanometers, or zero point zero 0.04, maybe 0.04 micron in size. So what you can see, I'm just trying to find out a laser
Yeah, yeah.
pointer. Yeah, okay, yeah, I got it. So this this is a membrane cross sectional area I have shown here. So these are the porosities. and the gray areas are the membrane material. So this is the feed side here, which is having a different, say, ions or minerals or TDS. And what we do in membrane distillation, we heat the feed to the to the temperature of say 75 or 70 to 80 degrees Celsius. So we increase all those, those who are chemical engineers can understand this. So we increase the partial vapor pressure of the feed size. And what this membrane does, it is a hydrophobic membrane, so it doesn't like water at all. So it rejects water, but it only allows the vapor molecules, water vapor molecules, to pass through these porosities or channels. So it is known as a Knudsen diffusion. And on the other side, we either have a vacuum or a fresh air at room temperature or very lower temperature. So it collects all those vapor molecules and it goes for a condensation. So it is a purely thermodynamic application. So this you can see in the market maybe 6 months from now. So what is good thing about MD membranes is that in contrast to RO, you're talking about hardly 1 kg or 1 bar pressure in the feed. And the other thing is your recoveries can go up to 90%. And as as we know the limitation in reverse osmosis membranes, for example, even if you take the ultra high pressure RO, where you talk about it can treat say up to 50,000 ppm TDS, and the maximum it can concentrate the feed is up to say 10%. So in membrane distillation you can go up to 35 to 40%. So up to the point where you can, where the precipitation of the salt starts. So you can go up to even that level of salt concentration. So now the fifth thing is the graphene RO. There is a lot of, there are a couple of international groups who are aggressively working on this. There is one US group who is claiming that they have these membranes already there. But so graphene membrane is basically a mono layer of carbon atoms, and whatever these hexagonal structures you see, this is a structural sieve or atomic sieve, which will basically separate all the say ions, mono ions or monovalent divalent ions or other impurities. But the problem, I mean, of course, the strength of graphene RO is that the extraordinary high surface area, mechanical durability, atomic thickness, high selectivity, and all that. But of course, still there are issues as far as the large scale production is concerned. There are, the low cost production is a very big challenge right now. But I think the way people are pursuing this, it seems like in couple of years time we should have this as a commercial solution, and then it can, maybe to begin with, it can focus on the high value added products where people can afford the high cost and all that. So the last part I'm going to discuss about on the membranes is the biomimetic membranes. Now see, now what we need to understand, the nature has given solutions to this problem, whether it is in the nature or in our body itself. So what, when I say biomimic means can we mimic the biology of the nature, or whether it is in the human body, and try to mimic that and come up with some membranes which, which represent the, say, the operations, like, body is taking care of what, maybe blood purification or any whatever we eat, whatever we drink and all. But our kidney is under use for, even if we take an average life of 70 years, so it is still under use without any, like, chemical wash, CIP, backwashing and all. So similarly our the cell membranes are filtering the the liquids, and they only allow the necessary amount or necessary the quality of water to pass into the cell, and they reject all the unwanted impurities. So two people have exploited that, and there is a protein or atom called aquaporin in the cell membrane or in our body, which basically allows only water to pass through and rejects everything else, and it allows the water to go through the cell, and that is how the moisture in the cell or water content in the cell is maintained. And there is a company called, it's a Danish company called Aquaporin. A lot of you might have heard about it or know, or you know the owner also. Recently they have gone for the public issue also. So they have exploited this fact, and they are collecting aquaporin from different plants or different natural sources, and they coat that aquaporin on their membranes, and they have come up with different, desalination membranes based on the aquaporin coating. On this picture I'm also showing a picture of Dr. Sidney Loeb, who he is the one who has invented RO. So around in 60s 70s, when he was inventing RO, the same time aquaporin was still working in his body. So this just to convey that nature is always doing its job. It is up to us to kind of pinpoint that or realize that, okay, how we can exploit it and how we can use it to solve the existing problems. So and of course there are people working on making more desalination more feasible. So combination of all these technologies or membrane based technologies I mentioned, you can mix all that and try to come up with the very feasible solution. You can, people have started already using the energy recovery devices. So ERD thing is already in the market since last many years. So yeah, that was based on the
Sunil, we lost you.
yeah. Can you hear me?
Nah, yes, now.
Okay, you can hear me now, right?
Yes.
Yeah. Let me take a sip of water. And so now I'll be. You can hear me, Chandu, right?
Yes, yes, we can.
Yeah. So the next, we are entering into the next part of the talk, which is non-membrane, which is non-desalination. So now there are a lot of people working on the nanotechnology based solutions, and that is mostly limited to the heavy metal removals. So these are either nanoparticles or these are nano waves, as shown here, whether alumina based, TiO2 based, or silver based. So, and these basically, I'm just going to show you one application here by the Indian Institute of Technology, Chennai. So, Professor Pradeep has come up with this innovative technology based on the alumina and silver. So, it again works under it works without electricity, and they claim all the arsenic from the water. So such solutions are available there. There are multiple solutions available like this. So I'm just mentioning here one. There are a lot of people working on the advanced oxidation technology. So of course, as far as the oxidation is concerned, disinfection of the water is concerned, we know that chlorine has been in use for many years now, maybe more than 100 years or so. But the problem with use of chlorine is that it forms trihalomethanes, and which is a toxic component for the environment also and for the human also. So there are many people working on the highly reactive radicals which can form in situ hydroxy radicals and can oxidize the impurities in the water and disinfect the water. So in non desalination part, we are not talking about any salt rejection or removal of minerals or TDS. So it is mostly related to how can we disinfect the water, how can we say take care of the chemicals in the water, or maybe biological non degradable impurities in the water. So advanced oxidation process, there are multiple things people are using, like ultrasonic sound people use. There is a Fenton reaction, UV based ozonation and all that. But today I would like to mention one very recent technology which Mr. Tate from Liquid Technology International Japan was talking about. He is our international guest today. So what they have come up with, they have found some natural ceramic source in Japan, which is somehow located to a very specific geological location in Japan, and they have formed a ceramic beads by using this material. So what it does, so it is doing oxidation of the impurities in the water, contaminated water, and it is a natural, I would say, oxidation process. And there is something called Peltier effect, which they are exploiting or generating by using this using these ceramic beads. So I would like to show you a 1 minute video on this. Yeah, yeah. Can you see, Chandu?
No, we just see your presentation only, not
Yeah,
video.
now
No,
just a minute.
you're putting another file or you're clicking the YouTube.
No, I'm just trying to open an YouTube.
Dr. Sunil, on in this share screen option, you have to choose the
Yeah.
screen.
So that's what I'm trying to do now. So where is that?
Yes.
Yeah. So that is how this looks like. I mean, there are beads. There has been some agitation in the column like that. So
Okay.
it naturally starts. It generates charge on these beads, and there are how it oxidizes the impurities and it reduces the scaling components, or say calcium, magnesium, all these scaling minerals it reduces. And they have achieved, like, if you talk about the recent trials they have done in India, so they have done some trials in West Bengal. So the feed water was having around 600 TDS ppm of the TDS, and after this treatment you get around 150 up to 200 TDS. So good thing about this is that just go back to the, so it is kind of a potential replacement for the ion exchange resins. And the good thing is that it doesn't need any recharging. So it's a, it can be operated in a continuous mode without any recharging or treatment in between and all that. And the minimum life they are claiming is up to 5 years, and it is already in use in US for different agricultural applications. So this is something I wanted to share today prominently. That's why I also invited Ted, who is representing LTI, so that he can come to know what all what all possibilities are there in India. Then there are people, there are technologies like pulse UV technology, which basically compared to the continuous UV, it releases the a certain amount of light, the UV light, with certain particular wavelength, but it is in the pulse formation, but it is supposed to be more efficient. It can have good microbicidal effects compared to the continuous UV, but still there are multiple claimants that were saying that no, this still the continuous UV is the best one, but I personally see there is a lot of potential in this. Yeah, just go to the laser pointer. Yeah. Now this is again some data, some reliable data I got on the pulse UV technology. So you can see at around 6 to 8 micro joules per centimeter square dose, you can get up to 6 to 7 log reduction of the bacteria. So this is something which is really picking up. These are some details. I will skip this. Now, while I was preparing for this talk, I came across this statement by the Sebastian Tillmans from the Codiga Resource Recovery Center, and this recovery center is mostly it's in collaboration with Stanford University. So they have put this based on the anaerobic bacteria, water treatment by using anaerobic bacteria. So what it says is the concept of waste doesn't exist in nature. Every byproduct of some natural process is an input for another. So as I was saying earlier in this talk, that the nature has solutions for each and everything. It is just that we need to pick up the clues and try to convert that into a usable form. So now this brings me to the last segment of the topic, or maybe the last segment of the non desalination non membrane treatment, so which is bacteria. Though right now we are scared of all the bacteria and viruses because of the COVID, but I'm going to talk about a very helping bacteria here. So again, this anaerobic technology, it personally I am a fan of this, and it seems like that it is going to solve many issues in the future. So though this slide looks very complicated and it's like a typical biology class slide, but don't try to understand it. What this slide is trying to convey is that anaerobic technology or anaerobic bacteria is something, a bacteria which can survive without the need of oxygen. So like we need oxygen, any living being like us need oxygen to convert our food into energy. This bacteria basically it just needs some electron to convert its food into energy. So what is the food for this anaerobic bacteria? The food is most of the impurities in the wastewater or any waste. And this bacteria has been there when the earth was shaping up, when there was no oxygen at all. So this fact was is exploited by the engineers and scientists from Stanford, and they have come up with the technology, water treatment technology based on these bacteria. So there are only 3 plants right now in the world. One is the Codiga facility in US, then South Korea has one plant, and now recently they are coming up with a big plant in Redwood City. So this is how it looks. As I said, not only the water, but it can treat any other any other waste, like coming from whether it is agro waste or wastewater or food waste. So this bacteria eats all the impurities in it, and then you get biogas also, and of course you get one of the product you get is that water which you can filter through through the membranes, and it can, of course, still not of the quality of drinking water, but it can go to the lagoons, and wherein you can try to at least maintain the water tables or replenish the aquifers. The good thing about, I mean, of course, we all know the aerobic technology, which we are right now using a lot of say bacteria based technologies which needs oxygen. When it needs oxygen, you need a lot of energy, because you need a lot of blowers to mix air into the water and to keep that bacteria alive. But this anaerobic technology or bacteria doesn't need oxygen, so you need very less energy because you don't need blowers or air, and the footprint is around 40% less. So I see a huge potential in this as far as the future is concerned, but this is mostly for, the community projects or treating the very large amount of waters. Now there is a group working on something called high tech filtration. Now here all the BJP supporters should get very happy, including me, because this is mostly talking about a treatment of manure coming from the cows. And the the cows are there worldwide, which makes this technology very promising. So what they do is they treat the manure or the cow dung, which gives you biogas, and then it also as a output, one of the byproducts, it gives you water, and that you can filter through different membranes, air strip and all that, so you can get a clean water. So to put some numbers on it, for example, if there is a dairy farm having 2000 cows, so you may ultimately end up getting around 40,000 gallons per day water, which again is not like a drinking water, but it can go to a clear water lagoon and you can try to replenish the aquifers. So similarly, the third and important thing which nature is giving us a hint or clue is a nitrogen cycle, wherein the bacteria use nitrogen to convert it into ammonia. Then ammonia converts into nitrates. Nitrates are consumed by water, by the plants, and then again it is released into atmosphere as a nitrogen. So these type of bacteria you can use to treat the water, so you can exploit this cycle also in order to treat the water. So I'm not going to discuss more detail about this, because I already talked about two bacteria. So this is how the nitrogen cycle should look like. This is the chemical different chemical reactions if you are interested in it. But as I said, we can go in one-to-one discussion if you are interested in this. So okay, I'll come to the very last part of it. It's around, I think, 5 minutes left for my talk. So this is how for example, future desalination plant look like. So we have water coming from the sea, which say around 3-4% of the TDS or salt. It goes to the pre-treatment, then goes to seawater desalination RO, then ultra high pressure RO. So right now we are limited to this portion only. So which gives you water with say 10 to 11% concentrated TDS or water with salt. Then this reject from the ultra high pressure RO will go to the preheater, which will be heated say up to 70 to 80 degrees, and then it goes to the membrane distillation module, wherein this reject is again concentrated to around maybe 35 to 40%, and you recover the clean water say with less than 100 ppm TDS, and the clean water which again coming from the RO unit, which is say less than 500 TDS. So that's how you increase the recoveries up to 90% or more than 90%, and the reject from the MD goes to a chloralkali process, wherein you get sodium hydroxide, hydrogen gas, and chlorine gas. So I just tried to do some number crunching on this concept on the Mijnoor desalination plant which is in Chennai or in Tamil Nadu. So there is a conventional plant right now. The capacity I don't remember, but I remember with the conventional process, the payback period is maybe up to 10 to 15 years time. If you try, I just tried to work out the numbers with MD and chloroalkali and all this. So if you put this, the payback period is up to 3 years. So anyway, this is just a concept which I'm throwing out of my mind just to present that how the future desalination plant would look like. So this just one concept on the membrane distillation base. So thank you so much, guys. I think that's all I had to share today. Maybe I can take few questions, or if there are detailed discussions you want to do, we can do those one-on-one. Chandu has my number. Thank you, Chandu. Thank you all. Thanks a lot.
Thank you, Sunil, for that showing us the future of water treatment with different kinds of innovations going on, and the timeline also you have put, something coming in 6 months, 3 years, 4 years, and so that's the one point. And just I would like to say one more thing. I think what he said about little bit a political word that he used. So that is something I feel that Sunil, you should have used the word livestock. So rather than mentioning let us take as a we have a good forum here. Let's take us this as a sportingly, and nothing is anything about political related affiliation. We don't talk about in this forums. So just take it lightly. I don't want that any further discussion should be on that. Let's focus on what is the what is there in that content is more important than some sideways to say that make it more interesting. So that is something I just wanted to clarify right away in the very beginning. And so obviously if you have any questions, and if you I don't see that in the chat box. uh, okay, somebody put that uh, request to share handouts, but I think we'll put this video on our WhatsApp group, so you can watch. And Sunil is there in the WhatsApp group, so if you have any questions to him directly, also you can ask him, and offline you can discuss with him, email him. All these details are there. Okay. Right away we have another 5 minutes, so if any have any questions, you can just unmute and ask him directly, please.
Hello.
Yes.
Hi. This is Varun from HSIL. So I need to know, is any Indian data is there where MD installations is working?
Yeah, it is in the Barun. Hi, it is in
Hi,
the
sir.
process.
How are you?
Yeah.
Yeah.
Good. So
Mhm.
it is in the process. You will see that maybe in next 3 to 4 months time. But as far as
Okay.
there are pilot plants already where people are working on it since last 1 year or so.
Okay.
Yeah.
Sure. Thank you.
Anybody else? Looks like people have future is you have made the future secured for everyone.
No problem. I think we should thank everyone. And
Yes, so looks like your presentation, if they have no question, that means that's why I'm saying that you have secured their future. And so thank you all our friends, and special thanks to Dr. Sunil Dhole for this wonderful presentation. And I request all of you that offline, if you have some other questions and want to discuss something more and all, he's there in our group. He's always in our group to help us with any technical. I have seen many a time some technical question. He's promptly, advises, and whatever he has. So I definitely look forward that use our Sunil as much as you can for the technical inputs. He's more than happy to do it, without thinking too many things in his mind. So I know him so well. So please ask, and so that you can benefit it by our technical aspects in WQIA industry fraternity group. So with that, I really wish everyone be safe, stay healthy, and as far as possible, you take care of yourself and your family, friends, and thank you all. Thank you, Sunil, once again.
Thank you all. Thanks a lot.
Bye.